Well, thank you. First of all, I would like to thank the organizers, particularly Barbara, for her kind invitation to this very interesting workshop. That said, my idea with this talk is to present you an integrated geophysical petrological approach to model the lithospheric uppermost mantle structure, and that from both a forward and inversion point of view. So I'll try to, first of all, justify why these sort of integrated approaches are interesting at all for the problem that we're considering, modeling the lithosphere, and then I will discuss a little bit of how forward modeling and inversion compare. I'll show you a synthetic example about the inversion part, so you get an idea. And well, this is more or less the outline. The work that I will be showing you here, it's of course not just mine. There are essential contributions from other people, as you can see in this list, mainly from GEMOC University, Macquarie, in Sydney, and also from the Dublin Institute for Advanced Studies in Ireland. So when it comes to model the lithosphere, what we mean is that we somehow want to connect observations that we make or collect at the surface or above the surface of the Earth, like topography, seismic data, mantle xenoliths, or satellite data with some sort of physical parameter that for us is meaningful in describing the Earth. For instance, from a traditional geophysicist point of view, this could be something like that: shear wave profile, or density profile, or electrical conductivity profile. What we would like to do with this integrated approach is to go a step forward and compute the variables that at the end are responsible for these secondary geophysical parameters and the very geophysical observables. And those are, of course, as we know, temperature, pressure conditions, and the composition of the mantle. To attack this problem, you have two possibilities. You can go for a forward modeling approach in which you assume something about the Earth and then solve the equations, compute the synthetic data, which are then compared with or against the real observations, or just directly an inversion, where you go from the data to the geophysical parameter. The two approaches or the two ways have their own advantages and disadvantages, and I'll try to comment on that a little bit later. But first, a little bit on the justification of why this integrated modeling is interesting. We've been hearing a lot about the lithosphere-asthenosphere boundary, one of the, if not the most fundamental discontinuity in the upper mantle, very much related to plate tectonics. And as we have heard, there are many definitions, as a more thermal, chemical, mechanical boundary. Those definitions actually depend on the physical property that you're focusing on. For instance, if you're looking at some seismic velocity or seismic anisotropy, you will be talking about seismic LAB, or if you're looking at electrical conductivity, then you will be talking about electrical LAB, thermal LAB, chemical LAB, and so on and so forth. The problem with these various definitions is that sometimes they are not exactly the same, and that can be a little bit tricky. If you think of it, some of those are really directly related. For instance, the mechanical lithosphere clearly is related to the temperature distribution, the amount of water, but also something else, as we've seen in the previous talk by Lars, for instance, the null hypothesis. This is a shear wave velocity profile taken from surface wave inversion in central Mongolia, and you can see, we have this low velocity zone, which, as Lars said, is just a result of the correlative variation of the temperature profile, which changes the slope here when you get into the sublithospheric mantle, plus the linear increase of pressure with depth. Of course, there's some attenuation as well. But what I try to say is that, in a way, the seismic LAB can be reduced to temperature, pressure, attenuation variations. Or if you have a look at this profile, this is an electrical resistivity profile from Cabell Creighton, actually. And you can see there's a low resistivity zone here, which we would traditionally interpret as the electrical LAB. But in this case, it's just the result of the temperature variation plus, as Anne has shown before, the water content distribution with depth that changes dramatically the electrical conductivity of the minerals. So in this case, electrical LAB can be related to temperature water. So what I'm trying to say in a way is that perhaps using this global or integrated approaches, we can unify LAB criteria, which I think it's surely a useful thing to do. Also, the fact that the geophysical data that we are using for our inversions or forward models, they have different sensitivities to temperature and composition variations, and that's through their dependence on, well, seismic velocities, densities, or electrical conductivities. For instance, if you look at these surface waves sensitivity kernels, this is in blue for Rayleigh waves and red for lobe, you can see how they are sensitive to VP variations, V wave variations, VS variations, density, and how that actually changes with the period. Or this other plot here, which shows you the topography or the elevation as a measure of the buoyancy of the lithosphere. You can see how that changes when you change the thermal thickness of the lithosphere. Normally what you would get is, okay, if you make the lithosphere thicker and then colder and then it's denser, well, the buoyancy will decrease, and this is what you see for most of the compositions. For some other compositions, for instance, this one on top of the plot, which is very, very much depleted with high magnesium number, well, at some point increasing the thermal thickness doesn't change the topography variation. This is because the temperature effect is trading off with the compositional effect of the depleted mantle. Finally, this gravity gradient sensitivity kernel computed at 255 kilometers above the sea level. The red line shows you the kernel for the vertical gravity gradient. And in here, basically what we have in the horizontal axis is the spherical distance from the observational point. The vertical behaves like gravity or geode anomaly, so the maximum sensitivity is located just below the measuring point. But however, for the vertical, horizontal, and the horizontal components, actually the maximum sensitivity is shifted from the computation point, the observation point, by actually more than 100 kilometers. So this illustrates how this different sensitivity works, which is great if you take all the data together. Of course, you will come up with a relatively robust model because you're covering most of the sensitivity that you can get from the data. And it's a warning, if you take them separately, you might end up with very different models of the Earth just because of these different sensitivities. I've mentioned that some of the LAB definitions could be related to, in the end, to temperature, pressure, compositional variations. I will just stop for one slide. On the thermal definition, we know that thermally the lithosphere is the part of the mantle where conduction is the main heat transport process, which means that from the global equation, and assuming a steady state, we can take out some terms, the advection term, temporal term, and you end up with a diffusion equation like that. Easy to solve, where you just have the thermal conductivity, radiogenic heat production, the source term, then by just fixing some boundary conditions, it's easily solvable. That effectively means that you somehow define a particular isotherm, 1300, 1315, something like that, above which everything is conductive, and then you have to relate that to the convecting sublithospheric mantle, where, well, we can use any isentropic or adiabatic approximation to compute the temperature. In between, we have a transitional or boundary layer in which, to some extent, the two processes, conduction and convection, take place. Of course, it's a challenge to parameterize this zone. Normally, what we do, or what people do, is to assume some smooth function or even a linear function. But in any case, I think we shouldn't expect any major thermal discontinuities in there. As for the composition, as we have heard before in the previous talks this morning, we need to somehow specify the bulk amount of the major oxides that compose the upper mantle. You can see a list here. This is interesting because once you specify the amount of those oxides, and as Lars has said, knowing something about the temperature and the pressure, you can compute physical properties in a self-consistent way. And also it gives you the possibility of, defining chemically the lithosphere, in the sense that people tend to imagine the lithosphere as something more depleted, incompatible elements with respect to the fertile sublithospheric mantle. So you can have this compositional dimension also included. As for the importance of knowing the bulk composition, if we can compute, assuming thermodynamic equilibrium, the Gibbs or free energy, and we can minimize that function, right? So we can obtain a number of properties about the system. So we can know what would be the stable mineral phases, the amount of these phases, volumetric amount of these phases, or the composition of these phases. And from here you can know things like densities or elastic moduli. So what is interesting about this integrated approach is that somehow you can connect observations made at laboratories or thermodynamic considerations with large-scale geophysical data, which actually allows you to answer questions like, for instance, how representative are the small portions that we analyze in the laboratory, the centimeters of the kilometric scale thing. With this approach, you can, well, take the values from the laboratories, put that into the equations, and then compute geophysical parameters and large-scale geophysical observables and see if that makes sense in terms of representativeness. Sometimes the other way around, there is a controversy about the importance and parameterization of the proton conduction term in olivine, that is a term related to the electrical conductivity due to the presence of water in olivine. And this has a huge impact of several orders of magnitude. You can see the difference between the laboratory groups from the black line values here and the red and blue lines. And actually in this example, what we did is to take very high quality magnitude telluric data from Campbell Creighton, plus some xenolith information on the temperature, pressure, and the composition, and we calibrated back those parameters here, the experimental parameters, actually finding something precisely in between the two experimental groups, perhaps very convenient. This is how a typical forward model works. So you start by defining lithospheric structure, then that means assuming some geometries, physical properties, thermal conductivities, composition, etc. First thing, you have to solve a temperature field. Once you know that, next step, solve the mineral equilibria equations, compute mineral assemblages and properties of the phases. Once you have that, you can compute bulk properties, like bulk density, bulk elastic seismic velocities, or electrical resistivities. Once you have this information in the volume that you're modeling, you can compute the geophysical observables. For instance, topography data, or gravity anomalies, gravity gradients, empty data, and so on. So you compare those predictions with the real data, and then eventually come back to the initial lithospheric structure, modify it accordingly till you get a residual that is acceptable. Good things about that is fast normally. If you think of a typical forward model, it runs from seconds to 2 hours if you want. So it's really not very time-demanding task that allows you to have a very detailed discretization in your grids. And this is good. Well, you can, for instance, if you have an idea of how to parameter, how the lithosphere in a particular zone of the world should look like, you can design an experiment, test it in a reasonable amount of time and see if that makes sense. On the downsides, it requires that you know a lot about the system. The potential parameter space is very large, composition and temperature. So every systematic exploration is going to be not possible. And finally, there might be human or modeler bias just because of the prejudices that people have or their backgrounds. So because of all those things, we started developing an inversion version of this already working forward model. This is what we've been doing recently, and I would focus on that now. We now are talking about probabilistic nonlinear inversion, where we are looking for potentially temperature, 5 or 6 major oxides, perhaps water as well. If you think of the size of a normal forward model, this is 50 by 50 nodes in the horizontal plane by 200 nodes, multiplied by 3.5 million parameters to invert for. So of course, any systematic approach is forbidden. There is the fact that the physical equations that we are solving are highly nonlinear, so we need some treatment of that. So now our parameter space is going to be described by a posterior probability density function, the sigma here, which basically depends on the a priori or prior PDF, the information that we have about the system before any consideration of the data, plus a likelihood function, which tells you how good a particular physical model is in explaining your data, and that also contains information, very relevant information about the uncertainties in both the data and also the theoretical uncertainties. So the uncertainties in the physical problems that you're solving and also in the numerical discretization that you're using, the grids that you're using. And this allows you to deal with things like, well, the well-known trade-off effects between temperature and composition, also the fact that temperature has a greater effect than composition for most of the observables that we're dealing with, and also an intrinsic non-uniqueness in the compositional field, which actually is worse in the lithosphere than in the sublithospheric mantle. For instance, if you have a look at these plots, this is a representation of the compositional space. Well, in this example, we're trying to recover specific VPVS values for this true composition here, and the other dots around are just possible compositions, the color telling you how well they are in reproducing the real values. So you can see whenever you're moving along those red areas, that means that you're essentially getting exactly the same VPVS and rho. So there's this intrinsic non-uniqueness that you have to deal with. As for the prior PDF, the previous information that you put into the model, what we did is to analyze a relatively large petrological database containing more than 2,900 samples, including mantle xenoliths, periodotite massifs, and ophiolites. We found some correlations which are actually independent of the age of the sample and the type of the rock of the sample, which allows us to explain or to determine some of the oxides as a function of, for instance, calcium oxide as a function of aluminum oxide, and the same for magnesium, which is good because it allows you to reduce the parameter space, the compositional space, from 5 potential major oxides to just 2, aluminum and iron. Then, when you look at the frequency plots for the database, and this is for aluminum oxide, and this is for calcium, you can see that there are things like 2 peaks in the density functions. This is probably due to the sampling of the database. For instance, we have much more information about Archean mantle and Phanerozoic mantle than we have for, say, Proterozoic belts. So this is probably behind these 2 peaks. So to avoid that, what we do is to have a very wide range of values, initial values for aluminum and iron oxides as independent variables, actually covering more than 95% of the total variability that we see in the samples. And then we assign a flat uniform probability density function to avoid any possible bias. Still, the resolution is too high. I mean, in terms of the time, you can't do it yet. So we have to go from the 200 vertical nodes to something like 6 compositional layers in the uppermost mantle, from the surface down to 380 kilometers. So we basically have these 3-4 compositional layers in the lithosphere and a couple of them in the sublithosphere, and 12 thermodynamic nodes, which are nodes in which we solve the the thermodynamic equations. Still, it's not enough. The problem is too big. We have to do something else. We split the 3D problem into 1D columns and inverting 1D data that are essentially 1D, that depend essentially on the vertical distribution of properties just below the computation point. For instance, surface wave dispersion curves or topography or even surface heat flow to first order depend on what you have below the measuring point. And then we use the posterior PDF functions taken from these 1D versions as prior information in the 3D. All these, of course, these PDFs that I am mentioning here are complex. They don't have any analytical expression. So when you want to sample them to put them into the inversion, you have to do some statistical independent approach. What we're doing here is a Markov chain Monte Carlo simulation for a random walk in the parameter space by basically using a Metropolis Hastings algorithm to go from one sample to another. In the case of the 1D inversion, we have actually 2 specific focuses. One, in the first part, we're just looking for the average temperature, the largest scale temperature distribution, and then for that we simplify the compositional space to just an average composition in the lithosphere and an average composition in the sublithospheric mantle. And then we invert for things like the LAB depth, which to large extent controls the temperature, the geotherm, and also the departures from steady state that we are assuming of more than 200 Kelvin. And in the second part, we use the information from the previous inversion for temperature. It's a prior PDF. And then in here we have the 6 full compositional layers. And well, we have PDF distribution for each compositional layer and for each oxide, potentially water as well. So let me show you an example, a synthetic example, to see how things work. So we have this, well, we have a lithospheric thickness, this synthetic model, which is a lithosphere which is somehow thick here, 170, 180 kilometers, thinning towards the northeast of the model, southeast of the model. We have 4 compositional domains, 2 depleted domains here with magnesium number of 93, and 2 fertile domains with compositional number 89.3. That with respect to a background value of 89.9, okay? So we have this moho, sort of periodic pattern. This is just random, is to avoid having just a flat moho. This is a 3D image, so you get a better idea of what we have. The red blocks are the fertile ones. So you have one here in the sublithosphere, one here in the lithospheric mantle, and the same for the blue blocks, which are the depleted blocks. So what we do is to compute the forward problem for this particular structure. So we compute things like the synthetic topography or the potential fields. We add a level of noise, and then we invert that back. I mean, we use that data as input in the inversion to see how much of this structure we are able to recover. This is what we get for the lithosphere-asthenosphere boundary, and this is the real model here, and the other 8 are just ensembles of 500 samples each, taken from the posterior PDF, which in this case is smooth and well-behaved with just one peak. And you can see that to the first order, we can recover most of the initial thermal structure. For a composition, things are a little bit more complicated. So, for instance, the posterior PDFs, the density functions are not necessarily smooth or well-behaved. But in any case, in here, I'm showing you an average because it's the only graphical way of representing it. So this is the true model. Now we're seeing results for magnesium number recover. And you can see that, well, in fact, the red blocks, which are the depleted blocks, are pretty much recovered. This is not the case for the fertile domains, which are blurred all around. But this is because, it's no surprise, because if you think of the distance in the compositional space in magnesium number units, for the fertile ones, it was less than 1 unit. For the depleted one, it was 3. So what this is telling you is that things like a unit in magnesium number, this is something that we can't possibly recover with this approach, given the uncertainties, intrinsic uncertainties in the data and also in the physical problems that we are solving. Finally, for the aluminum oxide, things are a little bit better. And here we do recover the depleted ones, the blue ones here, with low aluminum oxide content, but also to some extent the fertile ones. And this is essentially because aluminum oxide controls the amount and the composition of garnet, and garnet is the fastest, densest, and most conductive phase, electrically speaking, in the upper mantle. So it has a great impact in the geophysical observables. What that means is that from what we see from this test, aluminum oxide actually could be a better indicator for compositional anomalies than magnesium number, for instance. Okay, so to conclude, well, I hope I have somehow persuaded you about the strong points of these combined or integrated geophysical petrological approaches, where we actually try to avoid inconsistencies of dealing with the data sets independently, and also we exploit the different sensitivities of the observables to variations in temperature and composition. And in comparing, well, forward modeling and inversion, probably you got the idea that inversion is the future, it's the way to go, because, well, it doesn't require a lot of information from your side. It actually allows you to explore the compositional and temperature space in a reasonable amount of time, of hours, days, which is not so much if you think of the size of the parameter space. And in principle, if you have done things properly with the covariance matrix, you shouldn't have any specific bias in the inversions. On the downsides, of course, the resolution has to be lowered somehow, spatially speaking. But this is precisely what forward models are good at. They are relatively fast, seconds, minutes, hours, few hours. And therefore, you can get a higher resolution. So my final advice is to take the best of both worlds, right? So first go for an inversion and figure out how the main aspects of the temperature compositional space look like. Then perhaps go for some detail for modeling in high resolution to test other details. I think this is it. Thank you for your attention.